Last week on the At HPC podcast.
Hi, I'm Doug Black, and I'm with Shaheen Khan. And today we have a very special guest. We have Rick Stevens from Argonne National Lab, and our special topic today is AI for science. So, Rick and Shaheen, welcome.
That's the lesson, right? The lesson across these areas of science is that there's some combination of existing understanding, existing methods, accumulation of more data, models that show some capability to generalize, and the ability to integrate all of this and to train it, which needs a huge amount of computing. It's the combination of all of that that's going to result in this notion of AI for science making impact.
It's an incremental struggle, in other words.
It is, but it's also incredibly computationally intensive. At the end of the day, it's not like suddenly we're going to use these AI methods and we're not going to need supercomputers. We're going to need even more supercomputers,
Right.
both for training this, but also because we're going to want to expand the scope of what we can do.
That's where we left off last week. Today we continue the conversation with Rick Stevens on AI in science.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
So, Rick, we thought maybe we could start off with your background in this area, AI for science, your journey. When did this begin? And take us through it a little bit.
When I originally came to Argonne in the early 80s as a student, I worked on automated reasoning, which is the symbolic branch of AI. So I've been interested in this problem, this generalized problem of AI for decades. And of course, I had detours into parallel computing, into computational biology, into collaboration, visualization. I did all kinds of things, right? But if you go back maybe 7, 8 years ago, it started to become clear to us, not just me, but many of us in the field, that AI was starting to become interesting again around 2012 with the success of convolutional networks and vision and machine learning and deep learning in particular was looking like, we might be on another wave. And that was around the time that lots of things were happening. ImageNet was created a little bit earlier than that. There were competitions where deep learning started to make waves. And in one area of AI after another, various forms of machine learning or reinforcement learning, and particular deep learning, were taking over in traditional areas of AI research like planning and game playing and computer vision and computer speech recognition and things like that. And we started thinking, one of the reasons that I originally got into computing was the notion that we could build intelligent computers and we could use them to solve interesting, hard scientific problems. I was never particularly interested in replicating human behavior in things like vision or speech. I mean, lots of people were motivated by that, but I was never that particularly interested in that. Even in the problems when I was working on automated reasoning, we were applying that technology to solving theorems in mathematics, proving theorems. And we also started using that to design molecules. We were doing chemistry, started doing computational biology with it. And that was in the 80s, back when we had really wimpy computers and we had almost no data, and it was very hard. But it was clear back then that the approach that we were taking at that time that was kind of rule-based. You might remember the term expert systems, and in the mid-'80s, the Japanese were doing the 5th generation project, and there was a lot of concern that maybe there's a whole other way of doing computing that's different from what we were doing in the US. And I was fortunate enough to be involved in analyzing what the Japanese were doing. And we had a lot of collaborations, a lot of friends there. And ultimately, this idea of using logic as the basis for computing didn't pan out. And it didn't pan out for several reasons back then, because they were trying to build specialized hardware that worked fundamentally differently than the hardware that we had. And that was interesting. But the problem is that it wasn't competitive with general purpose hardware. There was so much gain coming from Moore's law in the 80s and 90s that any kind of specialized hardware was just not competitive. And we saw that in the Lisp machines. There was a burst of activity, and then they weren't competitive. We saw it with the Japanese. And so general purpose computing took off, riding Moore's law, parallel computing happened, and the AI people had a hard time getting funded, and they were working quietly in the shadows, right? And it was only in the mid-2000, 2010, 2005, 2010 timeframe, the things started to emerge. So to make a long story short, I mean, in the context of this notion of AI for science, this was a latent idea, for a long time, right? We were busy doing exascale computing. And I went back and looked at the original report that we created in 2007 that launched the US Exascale Initiative. And in that document, we don't mention AI once. And we barely mentioned data. It was really traditional modeling and simulation that was the vision in 2007 that was going to be the driver for everything. But of course, on the way to exascale, interesting things happened, right? GPUs were discovered to be good for AI. They were not designed for AI, right? It was kind of an accident that they were discovered. And deep learning took off. The tech industry started pouring money into frameworks, a lot of competitions, and suddenly AI was back in the news again. It was a good thing, it was something you could get a job in. And we started going back and saying, well, gee, this idea of building models in science where we don't have strong theory, like in biology or medicine, or even things like inverse design problems in material science or chemistry, maybe these problems now will become more tractable. We're starting to collect a lot of data, genome sequencing data, imaging data from the light sources. All kinds of data is being collected in science, data from telescopes, from microscopes. And so there started to be momentum in the scientific community about bringing machine learning to interesting problems in science. And I would say the interest is continuing to grow. The actual term AI for science and the kind of origins of the DOE initiative that we're working on, I would say, had their beginning in the spring of 2019, when we started looking at the fact that exascale seemed to be on a trajectory that was going to converge and land, and you're going to land the plane, maybe a little bit late, but we're going to land the plane, and what was going to follow that. And so three of us, myself, Jeff Nichols at Oak Ridge, and Kathy Yellick at Berkeley, worked with DOE headquarters, Barb Helen in the Oscar office, and we said, look, Barb, this was, I think, probably the first conversation around that was probably in March of 19. We said, we're thinking that there's a lot of interest in this. Why don't we hold some town hall meetings and just gauge how much interest there was? And so we planned 3 town halls with a fourth one that was going to be in Washington. So the first one was at Argonne in the summer, I can't remember, July or August of 19. And then we followed up at Oak Ridge and then at Berkeley. And the community came out like crazy. I mean, we had 1,200 people at these town halls. People were interested in applying AI from everything from designing materials for better batteries to designing drugs to accelerating climate models to feeding in all the data from cosmology observations to try to sort out dark matter and dark energy. I mean, just hundreds of ideas. And we organized those workshops on application themes, on infrastructure themes, and so on. And there was a great report that came out in February of 2020 that's on the web. You can find it. It's AI for Science. And we involved some of our division directors, Valerie Taylor and David Brown, and Barney McCabe helped work on that along with hundreds of other people. And that laid the picture kind of out. And then shortly after that, we were trying to move this pretty fast to try to position it to be a significant activity as a follow-on to the exascale computing project. And so there was a call for a charge to the Advanced Scientific Computing Advisory Committee, right, that recommends things for Oscar. And Tony Hay took up the charge and did a very fast, very deep, thorough analysis of what the opportunity was, talked to lots of people in industry and across the fields, different agencies, different parts of DOE, and recommended that we proceed. So that's how it got going.
Excellent. Rick, the incremental progress that you mentioned is also comforting in a way when you think about all the cautionary aspects of AI, about how it might create a false sense of confidence. And of course, as you mentioned, when you have too much data for humans to go through, or when the complexity goes beyond the ability of a human to tackle or track, then you're relying more and more on AI. So can you speak to that cautionary aspect of it and how the way it's panning out is going to cover for that, hopefully?
Yeah, so there's several aspects to what you're saying there. One is that we need AI approaches that allow us to interpret or understand what the models are doing. Sometimes goes by explainable AI or interpretable AI. That's one aspect of it. These very large models, like big transformer models, for example, for language that have billions of parameters in them, the only way we can really understand those is by treating them almost like research subjects themselves. And we kind of ask them questions and we probe them and so on to try to understand how they work. We need methods that are maybe easier and more transparent how they work. That's a tall order because we still want them to work well, right? Another one is ethics, or the thinking, ahead about what are the use cases of this model, and do we as reasonable people, are we prepared for what those use cases are and the unintended consequences of those use cases? So there's a whole ethical component to this. And then this is maybe less of an issue in science than, say, in other areas like policing or something like that, but there's bias. And bias, of course, is a technical term in the sense that the model's behavior is not precisely what we want it to be, whatever it is that we want it to be. It never is. The difference is always the bias. But do we understand the bias? And do we understand, again, this comes back to the use cases, the impact of the bias that's in the data or in the modeling approach, and what does it mean when the model is being used? These are all things that we have to get our head around. One of the things that we think is very important within the DOE context is this ethics, and sometimes security is another one that you put in there, because you need these models to be robust and secure and not easily faked and so forth. So there's a whole set of issues ranging from ethics to bias to security to robustness that needs to be part of the conversation, needs to be part of the research plan, the R&D plan, as well as how we evaluate these things. And even some of my colleagues are saying, well, if you cast this vision of AI for science out and you start having AI-driven robotic factories doing science, right? This is one of the things that we're trying to work on. What happens to the researchers, right? And so that's all part of what has to be discussed. There's a saying, and this has got various versions, but I'll just throw it out here just because it's kind of a fun. There's a saying that says, well, AI is not going to replace scientists, but at least not in the short term, but scientists who use AI are likely to replace those that don't, right? And this is the same concept applied to simulation or whatever, right? I mean, we need to use the best tools that humanity can create to work on the hardest problems. And when AI becomes the best tool to do something, whether that is in science or in medicine or in other areas of life, we kind of owe it to ourselves to work out how to use it and do it in a thoughtful way.
Right on. No different than using a laptop, really. Did it replace some? Well, I guess if you don't use computers these days, it's harder to participate.
Yeah. Rick, I guess my last question would be, are there areas of AI for science in one discipline or another where you're seeing tremendous promise to take on the big problems that the world yearns for solutions for?
Yes, for sure. There's a couple of them that I am particularly excited about. I mean, we talked a lot about surrogates because we're HPC and so forth, and I think there's going to be a lot of progress there, and that's going to effectively give us on our exascale machines things like zeta scale capabilities, right? So that's kind of cool. There's been huge progress in these large language models like GPT-3 and so forth that a lot of press has been about, and the labs have projects where we're trying to train those kinds of models, but now on huge amounts of scientific literature and underlying scientific data. No human can read 1 million science papers, right? In your lifetime, you might read, 50,000 or something. But, there's 100 million science papers out, at least 100 million science papers out there. And we'd like to build a system that can read all of that. And so every scientist who's working on a problem, in some sense, has the combined ability to bring all of the knowledge that's been accumulated over hundreds of years into that problem, right? And that's going to be some kind of system like what we're talking about. Something way better than a Google search, right? Something that can actually integrate concepts from the literature and that maybe can pose things as hypotheses that you could go test or as challenges for you to think about. So this idea of language models in science is going to be a big area. And then another one is in using AI to ease the coding burden. So as we're fielding exascale machines, right, we're rewriting millions of lines of code and reworking software stacks and so forth. And we'd rather, as the saying goes, we'd rather write code that writes code than write code, right? So this idea that AI, things like Codex, like the models that Microsoft and others are building, DeepMind's also got one, this idea that we can build AI models that can help us, say, adjust interfaces or that can port code that runs on one GPU to another type of GPU, or that basically can help us with the software burden. I think that's a major area. And of course, this idea of using AI to generate more AI models is another area that people are working on. And then finally, the holy grail, or one of the holy grails, not the only one, is this idea of what we call autonomous discovery, and particularly in areas that are dominated by bench science approaches like materials and chemistry and, say, molecular biology kind of areas, where progress is often through lots of experiments, lots of postdocs and grad students, with pipettes and stuff like that. Can we devise a way to automate science to the point where I can interact with the machine, give it high-level objectives, And it can devise the experiments, carry out the experiments in some kind of automated infrastructure, gather the data, update the models, maybe iterate a few times, and then come back and say, oh, well, you're interested in this new battery material. Why don't you try this one, and this one, right?
Mm.
And that kind of a autonomous laboratory, autonomous discovery, or sometimes we call them self-driving labs because people kind of get what that means. That has the potential of both accelerating research in many areas, whether it's for drugs or synthetic biology or materials or benign chemistry or new polymers that are safe for the planet and stuff like that. But it also potentially opens up science to many more people, because we separate the ability to talk and reason about the problem from who owns the infrastructure for doing the problem. Just like cloud computing kind of separates needing to do something from owning the hardware, this idea of an autonomous lab where you might have big robotic factories somewhere that are able to do science experiments means that you could suddenly flatten access to state-of-the-art scientific capabilities across the country by using these laboratories remotely.
So letting researchers be researchers and not so much technologists.
That's right. And that's a really hard problem, but there's a lot of interest in it. And if we can make progress in that, some of these big problems, like how we're going to decarbonize industry or decarbonize transportation to fight climate change, or produce a vaccine in 90 days from discovering a new virus or something like that. We're going to need this kind of technology to accelerate solutions to those kinds of problems.
Rick, my last question is about quantum computing, because just like AI, it also promises an entirely different net new tool for science. I know you guys are doing some activities in there in Argonne. What is the state, and would you be able to share any insights there?
Yeah, we're very interested in quantum computing and quantum information science in general, quantum sensing, quantum communication. It's all important. I think that it's probably on a longer timeline for impact than AI.
Yes.
But there is some coupling, right? So there are experiments that are being done with using AI, for example, to generate quantum programs or quantum gate transitions, or to optimizing a quantum circuit. As quantum computers get more and more qubits, the number of possible ways of actually programming a quantum computer to do something grows exponentially. And just like the burden of writing software we'd love to offload to the machine, I think the challenge, or maybe even some of the invention that we need to produce effective quantum algorithms, may be effectively exercised by AI, helping somebody write quantum programs. So we think that is potentially important. And of course, it may be possible, there's some theoretical results on this, but it may be possible ultimately that some machine learning methods could be accelerated with quantum algorithms. That hasn't really been demonstrated practically yet, but if one is dreaming, one can imagine that could happen. So there is a relationship there, kind of. I think it's on a long-term track. Of course, I keep saying AI early days there. There is going to be massive progress with existing AI methods because it's already being demonstrated to work. Whereas in the quantum case, we have to be patient and continue the investments and continuing to push the envelope there. But I think ultimately it will help. I believe that it's likely in the next 10 years or so that we will have more practical hybrid classical quantum machines that will start to be used for interesting problems. But we've got to get the whole landscape in quantum computing to kind of mature up a bit. There's a lot of hype on it, and
yes.
Some of the investment streams, it's not clear to me how they'll be sustained for a decade until there's real results. So I think we have to make headway there, but we also have to be, in some sense, moderated our enthusiasm, because the rate that we're investing relative to the new results, right, is somewhat modest.
That's a great way of putting it, and you're absolutely right. And my view is that the quantum computing guys want to avoid a quantum winter. That the AI guys didn't.
Yeah, exactly.
Yeah. Brilliant. Thank you.
Thanks so much, Rick, for joining us, and we hope we can drag you back to our podcast to talk about some other areas of your work in the future.
Oh, sounds great. I'd love to do it.
Fantastic.
Wonderful. Thank you, Rick.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.